Hello everyone, my name is Sumukha Bharadwaj. I'm going to present my paper on the title on the hardness of the determinant, sum of regular set multilinear circuits. This is joint work with S. Raja. We are from the Indian Institute of Technology, Tirupati, India. Our work is about the computation of polynomials. Polynomials appear at many places in computer science and mathematics. For example, the determinant polynomial is very common in linear algebra. The permanent polynomial can be used to count the number of perfect matchings in a bipartite graph. Now, it was shown by Valiant in 1979 that computing the permanent of a 0-1 matrix is sharply complete. Now, since the computation of polynomials is an important problem, we are interested in computing polynomials efficiently. The standard model for the computation of polynomials is the arithmetic circuit. The arithmetic circuit is simply a directed acyclic graph as shown. The leaves of this graph are labeled with either variables or some field constants. The internal nodes of the graph are labeled with either the plus symbol or the multiplication symbol. The internal nodes perform the operation with which they are labeled by. The polynomial computed by the circuit is the polynomial computed at the root of the circuit. Now, the size of the circuit is defined as a number of edges in it, and the depth of the circuit is simply the length of the longest directed path from any leaf to the root. Now, what are the typical questions that we ask in relation to arithmetic circuit? The first kind of question is, you're given a polynomial f, and we are interested in finding a small or a polynomial size circuit that computes f. The other kind of question is, we are given a polynomial f, and we would like to find the size of the low. We'd like to give a lower bound, that is the size of the smallest circuit that computes f. Now, the determinant and permanent are important polynomials in the study of arithmetic circuits. Let's define them. So let X be an n cross n matrix as shown. Here the entries of the X can be thought of as being variables. The entries of the ith row of X are going to be Xi, 1, Xi, 2, and so on up to Xi, n. The set of all variables in the ith row will be referred to as Xi. Now the determinant permanent are defined as follows, okay, as shown here. Now the summation is over the set of all permutations or bijections over the set 1, 2, so on up to n. They are defined very similarly. The permanent and the determinant are defined very similarly. The only difference is that the permanent does not take into account the sign of the permutation. Now, it was shown by Werkowitz in 1984 that the determinant can be computed by a small circuit. And one of the central open problems in the study of arithmetic circuits is to prove that the permanent cannot be computed by a polynomial size circuit. Now, although the determinant and the permanent are defined very similarly, there seems to be a huge difference in their complexity. Now, unfortunately, we haven't been able to prove strong lower bounds. That is, we haven't been able to come up with explicit polynomials that require super polynomial lower bounds. And so we impose the restriction of non-commutativity in order to prove strong lower bounds. So in non-commutative polynomials, variables do not commute under multiplication. That is, the identity xy equal to yx does not hold. Okay. So the non-commutative determinant and permanent are defined very similarly to the commutative determinant and permanent. The only difference here is that the variables do not commute under multiplication. A specific kind of the specific type of non-commutative determinant permanent is called as a Cayley determinant and permanent. Here the variable order is x1 followed by x2 followed by x3 so on up to xn. That is, in each monomial, the variable in the ith place comes from capital Xi. Let's look at the notion of set multilinearity. Let F be a field and let X be partitioned into the sets x1, x2, so on up to xt. Now, a set multilinear polynomial F with respect to this partition is a homogeneous degree D multilinear polynomial such that every non-zero monomial of F has exactly one variable from Xi for all I. Now, it's easy to see that the determinant and the permanent are set multilinear under row-wise partitioning of X. That is, you take the set of all variables in the ith row as Xi. Now, a set multilinear circuit is one in which each node computes a set multilinear polynomial with respect to some subset of x1, x2, so on up to xt. Now, it's an open question to find the set-multilinear arithmetic circuit complexity of the determinant. So in this paper, we look at a subclass of set-multilinear circuits called the regular set-multilinear circuits. Let me define the regular set-multilinear circuit, which will be abbreviated as RSM circuit throughout the talk. Now, the RSM circuits can be thought of as a commutative analogues of the non-commutative ordered circuits defined by Hrubes, Yehudayoff, and Wigderson in 2010. Now, the RSM circuit is a subclass of the set-multilinear circuits. So let X be partitioned into the sets x1, x2, so on up to xt, and sigma be any partition in st. So for any node v in an RSM circuit, okay, um, v computes a set multilinear polynomial with respect to some contiguous subsequence of sigma, and this contiguous subsequence will be referred to as order of v. Let's look at an example of an RSM circuit. So here you can see that for all the leaf nodes are labeled by some capital Xi. So for example, if you take this one, it is this leaf node is labeled by a variable that is coming from the set capital X1. So therefore, its order is going to be 1. Okay, and if V is a sum gate, then the order of V will be equal to the order of its left child, which is also equal to the order of the right child. And if V is a product gate, then the order of V is the order of its left child appended with the order of the right child. The root node's order is equal to sigma. Now we are particularly interested in this particular setting. We have k number of RSM circuits, okay, where k is a constant, and they're all RSM with respect to sigma 1, sigma 2, so on up to sigma k. We take their sum, okay, and the sum of these k circuits computes the commutative determinant. So we study the computational complexity of the commutative determinant computed by a sum of constantly many RSM circuits. So we show that if the degree n determinant can be computed by a sum of constantly many RSM circuits of sizes, then the permanent of slightly smaller degree can be computed by an RSM of circuit whose size is poly in S and epsilon is a constant. In other words, if there is a small representation for the degree n determinant in the sum of constantly many RSM circuits, then there is a small representation for the permanent. We need the following results. The first one is due to Erdős Székely from 1935. So let n be a positive integer. Let S be a sequence of distinct integers of length at least n square plus 1. Then there exists a monotonically increasing subsequence of S of length n plus 1 or a monotonically decreasing subsequence of S of length n plus 1. The second result we need is due to Arvind and Srinivasan from 2010. So for any n, if there is a non-commutative circuit C of size S computing the degree 2n Cayley determinant, then there is a circuit C prime of size polynomial in Sn that computes the degree n Cayley permanent. Now let's look at the simpler case, which is a sum of two RSM circuits. So X is a set of n square variables. If the degree n determinant is computed by a circuit C of sizes, where C is a sum of two RSM circuits C1 and C2, then the permanent of degree root n by 2 can be computed by an RSM circuit C prime of size polynomial in n and S. To prove this, we need the following lemmas, which we refer to as the reversal lemma and the composition lemma. Let's look at the reversal lemma. Now X is again a set of n square variables, and X is partitioned into the sets x1, x2, so on up to xn. Now let C be an RSM circuit with respect to a permutation sigma in Sn, computing the degree n determinant. Then there exists an RSM circuit C rev with respect to sigma rev, where sigma rev is simply sigma written in reverse, computing the degree n determinant. Moreover, the size of C rev is same as that of C. So C rev is constructed as follows. We simply take C and starting at the bottommost level of C, we swap the left and right child of each of the product gates. Okay? And the correctness is by a simple induction on the depth of C. Let's look at the composition lemma. So we have C, which is a sum of two RSM circuits, C1 and C2, computing the degree n determinant. Now, for any permutation tau in Sn, there exists another circuit C prime such that C prime also computes a degree n determinant. C prime is also a sum of two RSM circuits that are RSM with respect to tau composed with sigma 1 and tau composed with sigma 2. And the size of C prime is at most 1 more than the size of C. Now, construction of C prime is as follows. For every variable xij in C, we substitute the variable x tau of I comma j. Okay, and if the sign of tau is -1, then we add a node labeled -1 and multiply the root node of C with this leaf node. And this is due to the fact that the sign of the composition of permutations is equal to the product of the signs of the permutations. Now back to the theorem, we had C, which was a sum of two RSM circuits, and we wanted to show that if C computed at the degree n determinant, then the permanent of degree root n by 2 can be computed by an RSM circuit of size poly in NNS. Now we can, without loss of generality, we'll assume that sigma 1 is the identity permutation. Okay. If that is not the case, then we can use the composition lemma. That is, we can compose the sigma 1 with sigma 1 inverse to ensure that C1 is RSM with respect to the identity permutation. Okay. So we get a new circuit now, which is C hat. We'll look at the second circuit C2. So in the permutation sigma 1 inverse composed with sigma 2, there is a monotone subsequence of length root n. This is due to the Erdős-Székely theorem. Let A be the set of indices in that monotone subsequence. Now either the subsequence is either monotonically increasing or monotonically decreasing. In the first case, as sigma 1 is the identity permutation, the same subsequence of indices in sigma 1 is also increasing. So for all j that does not belong to n, we set the variable xj comma j to 1. And for all I in n such that I is not equal to j, we set xj comma I and xi comma j to 0. Okay. So now we can ensure that the circuit C prime computes the determinant of degree root n by suitably renaming the variables. Okay. Now C prime is also going to be RSM with respect to the identity permutation. And the size of C prime is at most 1 more than the size of C. So in this case 2, we can use reversal lemma and modify the circuit C2 to get an equivalent circuit that is RSM with respect to the permutation sigma 2 rev. Okay. Now in sigma 2 rev, right, the corresponding subsequence now becomes increasing. So this is now case 2 is now reduced to case 1. And finally, on the circuit obtained, we are going to use the result of Hrbin and Srinivasan to compute the permanent of degree root n by 2. Now, how do we extend this to the case of sum of constantly many RSMs? Okay. So we have C, which is a sum of k many RSM circuits, and C is of sizes. C computes the degree and determinant. Then there exists an RSM circuit whose size is at most s plus 1 that computes the determinant of degree n to the epsilon, okay, where epsilon is at least 1 by 2 to the k minus 1. Okay, we can assume that the k RSM circuits here, they all follow distinct permutations. Okay, that is sigma I is not equal to sigma j for all I not equal to j. So now we have C, which is a sum of k RSM circuits. We refer to C as a k regular circuit. Okay, so so C looks something like this. Okay, so it is a sum of k RSM circuits, where each of these k RSM circuits follow a distinct distinct permutations. Now the idea is to recursively apply the sum of two RSM circuits theorem on C. That is, first we are going to look at C1 and C2 and apply the sum of two RSM circuits theorem. Okay, so this will ensure that now this will give us a circuit which is k minus 1 regular. Now we sort of recurse until C becomes 1 regular. So after the first step, we are going to get a determinant whose degree is n to the 1 by 2. After the second step, we get a determinant whose degree is n to the 1 by 2 square, and so on. So this recursion can go for k minus 1 steps. So at the end of k minus first step, we are going to get a determinant of degree n to the 1 by 2, n to the power of 1 by 2 to the k minus 1. Okay. So in each step, we are losing the degree reduces by a factor of root n. Now finally, on the circuit obtained, we use Hrbin and Srinivasan's result to get the permanent of degree n to the epsilon by 2. Now, where do we go from here? So the first question is, can we extend the result to sum of non-constant number of RSM circuits? Okay. And the second question is the bigger question, which is, what is the complexity of computing the determinant using the general set multilinear circuits? These are the references. Thank you.